Guys, welcome to chapter 15. We're going to do integration, a lot of integration in this chapter. Begin with section 15.1, double integral over rectangular coordinate or region. This region here. Okay, so what does this one look like? Let me just draw it out. So we have a rectangular region. It's gonna be some region like this. It is what they mean by rectangular region. Let's say the region D or the domain is a rectangle. What is this double integral over a rectangular region? Well, we have a surface over the region D. So we have a surface. Let me do a surface here, some ugly surface here. Let's say that we have this surface right here. D5 over region D. Okay, so this the region D. Well, we can form a solid S by connecting the region D to the surface. Let's do the connection here. The solid is gonna be that's V. Well, we have to do the base times height, right? So it's the sum of all base times height. Okay, so sum of all base times height. If sum of all up or over region D. Okay, so that is it. Well, we know the sum is the integral over the region D. So, well, we integrate with respect to x and y. So that means we're gonna have a double integral instead of one integral. Right? Okay, the base here. What's the base? What's the height? Base. I'm just gonna do a sample one here. dA, which is the change in x, change in y, and then you have a height. the sample volume. Okay, so the sample volume is the height, is the surface, right? Fxy, and then the base is going to be dx dy or dA. This is it. To evaluate the double integral, we used the Fubini theorem. Fubini is an Italian mathematician. Well, Fubini is the first mathematician that discovered this. So he discovered that the double integral over the region D. In the textbook, they write R, but then I'm going to write D for the domain, so that you can see D as the domain, because the region D has to be in the domain of the surface. This equal to, well, we haven't cut this thing out yet, but then now I'm going to cut it out. Right? X that can go from A to B. Right? So let's say that we have a to B here, right? And then for Y in general, it's going to go from C to D. Somewhere it's going to be C, and then D. So if you sum area of a cross-section slide over the y-axis, then it's going to be sum over the y-axis. So it's going to be from C to D. And then here's going to be area of a cross-section slide perpendicular to the y-axis. Or you can do this way. A to B, you sum the slide area of cross-section slide perpendicular to x-axis. Once you notice this one is C to D, right? The area of cross-section slide perpendicular to the y-axis is going to be a integral. Look at the slide here. It has the height of the surface, right? Oh, and the width is the small change in x. Say, so fxy dx, right? And then we got to get that area. So it's going to be A to B. So that is the area of the cross-section slide perpendicular to y-axis, and then outside here it could be dy. Okay. Next one is similarly A to B, area of cross-section slide perpendicular to the x-axis is gonna be integral C to D. The height fxy, the width is dy. So example, evaluate double integral d x squared y dA, where D is the region bounded by the rectangle. Zero less than equal x less than equal 3. 1 less than equal y less than equal 2. So I'm going to do a dx dy here. So if I do x squared y dx dy, meaning that the inner integral is going to be the area of the cross section slide. So x go from 0 to 3, and then the outer one is just the summing of the cross the area of the cross section slide. So y go from 1 to 2, and then based on Fubini theorem, so you have to do inside first and then outside. If you integrate with respect to x, right, you treat y as a constant. It's very similar to how you find the partial derivative. We integrate with respect to x there, so it's going to be x3 over 3 y. Evaluate this from 0 to 3. 1 to 2, right? 3 times 3 to 3, so 3 square y, that's going to be 9 y and dy. Okay, so 9 y squared over 2, 1 to 2, run out of room here, so I'm gonna 9 over 2, 2 square minus 1 square. So 9 times 3 is 27 over 2. Notice that fxy equal x squared y, which is x squared times y. And this can be seen as gx times hy. Yeah. If this is the case, then we can do this one. The integral 1 to 2, 0 to 3, x squared y dx dy. We can split this into an integral in x and an integral in y. So it's the x, right? 0 to 3, x squared dx, 1 to 2, y dy. You can actually do this, and then you see that you get the same answer here. Nine times it's the same thing too. 3 over 2, right? 27 over 2. Here come another example, right? Just evaluate for now, right? Evaluate. Well, the textbook used R for rectangle. You can use R or D, right? When you get to the later chapter, they just use D. So you can use R, but then if you write R, then you got to define R. Okay, so it's going to be y sine x y, right? dA. where r is, well, the set of x, y in which 1 less than equal x less than equal to 2, 0 less than equal y less than equal pi. Should we should we set up dA as dx dy or dy dx? Dx dy looks similar. So y psi x y dx dy. Okay, so x go from 1 to 2, y go from 0 to pi, and then I'm just gonna work it out. Right? I don't have enough room here, so I'm gonna work it out this side here. 0 to pi. Okay, so the integral of psi is cosine negative cosine. It's negative cosine. X, y, and then the other one they just cancel out because the u is the x, y, so the u is just y, and you divide both sides, you get rid of that y. So 1 to 2 dy. Okay. 0 to pi, we have a negative cosine. Ooh. 2y minus minus going to be a plus cosine y. Now it look better. Is everybody okay with the u sub here, right? Yeah, you can quickly do the u sub here. So maybe a little review here. U sub, right? U is equal to x, y, so du is going to be a y dx, and well, you see that the y dx is going to be du, and so that is why you have this one, right? And then derivative of sine negative cosine. Yeah, and this is much faster to do. So similarly, right, you're going to use the u sub, and then derivative of cosine is sine. Derivative of sine negative cosine. So it's going to be a negative 1 over 2 sine 2y plus sine y and 0 to pi. Oh, but then look at her. This sine. So you plug it in, you're just going to get 0 because this sine. Find the volume. Yeah. Of the solid as bounded by the elliptic paraboloid. Two x squared plus y squared plus z equal 27. The plane x equal 3 and y equal 3, and the 3 coordinate plane a little sketching here because I like sketching. Okay, so we have the plane x equal 3, right? Don't draw the plane x equal 3, it's just 3, y equal 3, right? And then it's gonna be bounded by the 3 coordinate plane, so it's gonna be bounded by x, y, z here. What do we have? We have you can actually get the surface there, right? The 2 plane and then the surface there, you know, is a paraboloid. The 2 plane, they're gonna intersect each other, and you're gonna get this. That is a rectangular region here. So the paraboloid up here is gonna be 27 because at x and y equal to 0, you get 27. Well, this is elliptic paraboloid. You know what a paraboloid look like, right? So it does look something like this. Base right here, right? That is the dA, and then you go up here. You go up to the saw somewhere, right? Go up here. That is the surface there. It's the height equal z. The height is z. So height times base area, that is the volume. From here, hopefully you see that the volume is the double integral over the region D. That is the region D right here. The height times the base area. Yeah, it is better if you remember the volume this way than just to blindly remember the formula. So a base area is up to you guys, right? You can either do dx dy or dy dx. So, but it's the same thing. There's just a square here, so 0 to 3, 0 to 3. The height is z, so we know z is 27 minus 2x squared minus y squared. And then the base area is, well, and then you can work it out. Oh, actually, let me give you the answer here. Yeah, you can check the answer. 162.